Evaluating limits analytically. Consider the two functions f of x, which is x minus 3, and g of x, which is the rational function x squared minus 6x plus 9, all divided by the quantity x minus 3, as x approaches 3. From the graphs, we can conclude that the limit of f of x as x approaches 3 is indeed 0. And the same actually holds true for the limit of g of x as x approaches 3, even though there is a hole or g of x is undefined at the x value of 3. But what if we're not given a graph and we're just given the function, say f of x is equal to x minus 3? What could we do to find the limit? Well, substitution is one of the fastest and easiest ways to find limits. So the limit of f of x as x approaches 3 is equal to the limit of x minus 3 as x approaches 3. So we're going to take this 3 found in the limit and substitute it in for x, and we get 3 minus 3, which is equal to 0. Now let's look at a couple more examples. Evaluate the limit of 3x as x approaches 0. Using substitution, we find that the limit of f of x as x approaches 0 is equal to the limit of 3x as x approaches 0. So we're going to substitute 0 directly in for x and get 3 times 0, which is equal to 0. In general, finding the limit of any polynomial function can be found by substituting the c value that x is approaching directly into the polynomial function for x, or evaluating the function at the c value. However, there are several theorems with well-behaved functions that make substitution faster for us. Let k and c be real numbers, then the following limit properties exist. The limit of k as x approaches c, where k is basically a constant, is equal to k. And the reason that this is true is because there's no x value that we can substitute c in for. So the constant is going to remain the same. The second property is the limit of x as x approaches c is equal to c. And the last one that we have is the limit of x raised to the k power as x approaches c is equal to c raised to the k power. Evaluate the limit. The limit of 7 as x approaches 6 is what value? Well, 7 is a constant, so to evaluate the limit of a function that has a constant in it, we can use the first property that states that as x approaches any value, the limit is equal to the constant value of the function, or the limit of k as x approaches c is equal to k. Now let's evaluate this limit. The limit of x as x approaches 9. To evaluate this limit of the function x, we can actually use the second property that states that as x approaches any value, the limit is equal to that value when substituted. In symbolic terms, the limit of x as x approaches c is equal to c. Evaluate the limit of x cubed as x approaches 2. Let's see what it is. To evaluate the limit of this function x cubed, we can use the third property that states that as x approaches any value, the limit is equal to that value raised to the same power. Or in symbolic terms, the limit of x to the k as x approaches c is equal to c raised to the k power. So we have 2 raised to the third power, which is equal to 8. Below are some more theorems of useful properties of limits. Let b and c be real numbers, and let f and g be functions with the following limits. The limit of f of x as x approaches c is equal to L, and the limit of g of x as x approaches c is equal to k. Our first property says that the limit of some real number b times the function f of x as x approaches c is equal to b times L. Now, why is this true? Well, think of b as a real number or a coefficient that's being multiplied by the function f of x. We can actually factor it out of this limit expression and write it as b times the limit of f of x as x approaches c. And now we will have b times, well, the limit of f of x as x approaches c is L. So that's why this is true. Now let's look at our second one that we have here. It states that the limit of the quantity f of x plus or minus g of x as x approaches c is equal to L plus or minus k. Now in this case, you could think of the limit expression as x approaches c as an extra coefficient that's outside of a polynomial that you can distribute through. So you can actually rewrite this initial expression as the limit of f of x as x approaches c plus or minus the limit of g of x as x approaches c. And then if we evaluate both of these, we know that the limit of f of x as x approaches c is equal to L, and then we have the plus or minus in between, and then the limit of g of x as x approaches c is equal to k. So that is why this is true. Let's try evaluating this limit with some of the properties that we just learned. We're going to find the limit of 3 times the quantity x plus 1 as x approaches 2. To begin evaluating this limit, we're going to use the first property, which says that the scalar multiple of 3 can be moved out into the front before the limit expression. And now we have 3 times the limit of the quantity x plus 1 as x approaches 2. Then we can use the second property to separate the terms prior in the addition problem. So we are taking the limit of x as x approaches 2 and taking the limit of 1 as x approaches 2. Well, now we know that the limit of x as x approaches 2 is 2, and we know the limit of 1 as x approaches 2 is just 1. And then if we evaluate this expression, we'll have 2 plus 1, which is 3, and 3 times 3, which is equal to 9. So again, we use the first property and the second property. And note, direct substitution would also work. Now let's try to evaluate the limit of 5x squared minus 3x plus 2 as x approaches 4. We're going to start by first using the second property to separate the terms first and take the limit of each term. So we can rewrite it as the limit of 5x squared as x approaches 4 minus the limit of 3x as x approaches 4 plus the limit of 2 as x approaches 4. Then the first property can be used to move each scalar multiple to the front. So the 5 and this 3 can be pulled out of the limit expressions there, and it can be rewritten as 5 times the limit of x squared as x approaches 4 minus 3 times the limit of x as x approaches 4 plus the limit of 2 as x approaches 4. Then we can find the limit of each of these and add them or subtract them together. So we can substitute the 4 directly in for x in x squared. We can substitute 4 directly in for x here. And the limit of any constant as x approaches another constant value is just the original constant. So that's how we get this expression, 5 times 4 squared minus 3 times 4 plus 2. And now we can evaluate it. So we're going to have 5 times 16, which is 80, minus 12 plus 2, which is equal to 70. So again, we used the scalar multiple being pulled out first, and then we used the addition and subtraction property. Also, direct substitution can work to help you solve this problem.
Below are the remaining theorems we will be using. First, let C be a real number, and let n be a positive integer, and let f and g be functions with the limits, the limit of f of x as x approaches c is equal to L, and the limit of g of x as x approaches c is equal to k. The third property states that the limit of f of x times g of x as x approaches c is equal to L times k. Now, why is this true? We can rewrite this expression as the limit of f of x as x approaches c times the limit of g of x as x approaches c. And when we evaluate each of these individual limits, we get L times k, which is exactly what this property states. Now let's look at the next one, number 4. The limit of f of x divided by g of x as x approaches c is equal to L divided by k, where k cannot equal 0 because you can't have a denominator of a fraction be 0. So now why is this one true? Well, the reason why this is true is similar to with multiplication and with addition and with subtraction. You can put the limit in both the numerator and denominator of our fraction. So we can rewrite it as the limit of f of x as x approaches c divided by the limit of g of x as x approaches c. And when we evaluate both of these, we will get L divided by k. And the last problem that we have here, or property, is that the limit of f of x raised to the n power as x approaches c is equal to L raised to the n power. Well, we can rewrite this as the limit of f of x as x approaches c, this whole quantity raised to the n power. And when we evaluate the limit of f of x as x approaches c, it is equal to L, and then L is raised to the n power. Now let's try to evaluate the limit that we have given here with the properties that we've been provided. We are finding the limit of 5x times the square root of x minus 1 as x approaches 5. When we begin to evaluate this limit, we can first notice that we have a product of terms here. So we can split this up and write it as the limit of 5x as x approaches 5 times the limit of the square root of x minus 1 as x approaches 5. Then the first property can be used to move each scalar multiple to the front. So we have this 5 that's in front of the x, so we can move that one out to the front. So we have 5 times the limit of x as x approaches 5 times the limit of the square root of x minus 1 as x approaches 5. And now we can evaluate our limits and then multiply our factors together. When we substitute 5 in for x, it's going to be 5. And then we can multiply that by 5 and get 25. And when we substitute 5 in here, we'll get 5 minus 1, which would then be 4, and the square root of 4 is 2. So we have 25 times 2, which is 50. So we used the third property, which is the product property, and we also used the scalar multiple by pulling it out. Note, direct substitution would also work. Now let's try to evaluate the limit of the quotient 5x plus 1 divided by the quantity 2x minus 1 as x approaches 3.
To start evaluating this limit, we first need to show how, when evaluating it, we need to take the limit of the top and the limit of the bottom. And that's using the fourth property of our list. Next, we can take the limit of each term in the numerator and each term in the denominator using the second property, which is the limits of addition and subtraction. In other words, these two properties. The next property being shown from here to here is the first property, which is used to move each scalar multiple to the front. So we can put the 5 in front of the limit of x as x approaches 3, and we can put the 2 in front of the limit of x as x approaches 3 in the denominator. Then find the limit of each before multiplying by the scalar, and then you can divide. So again, we use the first property, and then we finished evaluating it. Note, direct substitution would also work with calculating the limit of this expression. Next, let's try to evaluate this limit. The limit of the quantity x plus 3 squared as x approaches 5. To begin, we're going to use the last property of finding a limit when it's raised to a power. So the first step of that is to bring the exponent outside of the limit. Then the second property is used to take the limit of each term. So we rewrite the limit of x plus 3 as x approaches 5 as the limit of x as x approaches 5 plus the limit of 3 as x approaches 5. And then we can evaluate and finish finding the solution. We can use direct substitution right now to fill in the 5 for x, and the limit of any constant is still that constant. So we have 5 plus 3, quantity squared, so that's 8 squared, which is 64. And again, the properties used were the last one and the second one. Note, direct substitution would also work.